Imagine a math equation that can recognize your face, drive a car, write an essay, and recommend the perfect meme, all without ever being told the rules. That's not magic, that's a neural network. And today we're going to open it up, poke around inside, and figure out how this thing actually, thinks. And by the end of this video, you'll understand artificial neural networks better than 99% of people who use them every day. I'm Dr. Dude. Let's abide and get in it. Right now, artificial neural networks, or ANNs, are everywhere. They decide which videos you see on YouTube. They help doctors read x-rays. They translate languages in real time. And yes, they're behind a lot of the AI that's suddenly everywhere. But here's the wild part. At the core, an artificial neural network is just a huge pile of numbers being multiplied, added, and nudged over and over again. So in this video, we're going to answer 5 big questions. What even is a neuron in AI? How do lots of neurons become an artificial neural network? How does a network actually learn from data? Why did neural networks suddenly get so powerful? And what are they not good at? If you stick around to the end, you'll be able to explain artificial neural networks to a friend without saying it's complicated, and you'll see why these systems are more like pattern-hungry parrots than evil sci-fi brains. Let's start small, like single neuron small. This little circle we're going to talk about is an artificial neuron. Forget biology for a moment. In AI, a neuron is just a tiny calculator that takes some input numbers, mixes them together, and decides whether to fire or not. Imagine we're trying to decide if a picture is a cat. Our inputs might be how pointy are the ears, how round are the eyes, how fluffy is the body. Each of those things becomes a number. Inside our neuron, each input gets a weight. Think of weights as little volume knobs. If pointy ears are a strong cat signal, that gets a big positive weight. If something is very dog-like, that might get a negative weight. The neuron multiplies each input by its weight, adds them all up, and then adds a little extra number called a bias, like its personal threshold. So it's basically doing input 1 times weight 1, plus input 2 times weight 2, plus input 3 times weight 3, plus the bias. Then it passes that sum through an activation function. That's just a fancy name for turn this raw number into a nice squashed output, maybe between 0 and 1. If the result is close to 1, the neuron is saying, I'm pretty sure this is a cat. If it's close to 0, it's saying, probably not a cat, maybe a potato. One neuron by itself is not that impressive. It's like one brain cell trying to do your taxes. But the magic happens when we use a lot of them. A neural network is just a bunch of these neurons organized into layers. The first layer is the input layer. That's where the data comes in. If it's an image, maybe each pixel becomes a number. If it's audio, each small slice of the sound wave becomes a number. If it's text, each word or token is turned into numbers. Then we have hidden layers. These are where the interesting transformations happen. Each neuron in a hidden layer takes the outputs of the previous layer, multiplies them by weights, adds a bias, and applies that activation function. Finally, we have the output layer. That's where we get our final answer. If we're just doing cat versus not cat, there might be one number that represents how cat-like the image is. For more classes, cat, dog, car, toaster, you might have one output neuron for each possibility, and the network tells you the probability for each. Each layer takes the outputs from the previous one, mixes them with its own weights and biases, and spits out new numbers. It's like a big factory assembly line. The first station looks at raw pixels. The second station starts detecting edges and simple shapes. The next station starts recognizing eyes and ears, and later stations recognize whole cats. The cool part is, we don't program those steps directly. The network discovers them while it's learning. So how does this pile of math actually learn anything? Training a neural network is like teaching a kid to recognize cats, except the kid is terrible at first and you have millions of cat photos. Here's the basic loop. Step 1, start dumb. At the beginning, all the weights are random. The network looks at an image and basically guesses whether it's a cat or not. The guesses are terrible. It's chaos. Step 2, compare the guess to reality. For each image, we know the correct answer. Cat or not cat. We measure how wrong the network is using something called a loss function. You can think of the loss as a number that says, your guess was this bad. Step 3. Backpropagation. This is where we work backwards through the network and figure out how each weight contributed to the error. If a particular weight made us more wrong, we tweak it in the opposite direction. This process of passing the error signal backward through the layers is called backpropagation. Step 4. Gradient descent. We don't just wildly change weights, we nudge them. Gradient descent is an algorithm that tells us how to adjust each weight to reduce the loss just a little bit. You can picture it like standing on a bumpy hill of error and taking small steps downhill toward the lowest point. Step 5, repeat. We do this over and over and over with lots and lots of examples. Show the network an image, let it guess, measure how wrong it was, adjust the weights, next image, guess, compare, adjust. Over time, the network gets better. After enough cycles of this, the network stops being a terrible random guesser and becomes very good at mapping inputs, like images to outputs, like cat or not cat. In other words, neural networks don't know what a cat is the way you do. They just become extremely good at recognizing the patterns that tend to show up in images we humans label as cat. They're professional pattern recognizers with no idea what a whisker feels like. Now, when we started stacking more layers, going from just 1 or 2 hidden layers to dozens or even hundreds, we entered the era of deep learning. Deep networks can learn low-level features in the early layers, like edges and simple shapes. Middle layers can learn more complex things like eyes, noses, paws. Higher layers can learn concepts like cat face, dog body, or stop sign. This same idea is used not just for images, but for speech, for text, for game playing, and more. There are specialized architectures, like convolutional neural networks for images, recurrent networks and transformers for sequences like text. But the core idea is the same: layers of neurons that learn to transform data step by step. Deep learning got huge because 3 things came together at the same time. We got a lot more data, we got much faster hardware, especially GPUs and specialized chips, and we got some clever architectural improvements. Same ingredients as before, just scaled way up. So with all of this, are neural networks actually thinking? Not in the human sense. They don't wake up and decide, today I feel like recognizing cats. They don't have goals, desires, or self-awareness. They don't understand the world the way you do. What they're doing is taking massive amounts of data, finding patterns and correlations, compressing all that into a huge set of numbers, those weights and biases, and then using those numbers to make fast predictions when new data comes in. It looks like intelligence, especially when the patterns are rich and subtle, but under the hood, it's math all the way down. Here's the key idea I want you to remember. A neural network is a pattern compression machine. Imagine you have millions of cat and non-cat images. Instead of memorizing every single picture, the network learns a compressed representation of what makes a cat in general. It doesn't store photo number 1, black cat on couch, photo number 2, orange cat on floor, and so on. The network learns more abstract things like ear shape matters, whiskers matter, fur texture matters. Certain combinations of shapes and colors often mean cat, and random background noise doesn't matter so much. All of that information becomes encoded in the weights. When a new image comes in, the network runs it through this learned cat detector it has built into its parameters, and it spits out a probability. From chaos, millions of messy, varied images, the network extracts structure. It builds an internal map of which patterns tend to go together. That's not consciousness, but it is a powerful kind of compression and generalization. It's a way to turn huge, messy, high-dimensional data into something a machine can act on quickly. And this same idea extends to many domains: images, sounds, text, sensor data, you name it. That's why the same basic neural network idea shows up in so many different AI systems. But here's the twist. The same thing that makes neural networks powerful also makes them risky, because they are so good at pattern recognition. They will happily learn any patterns in the data, even patterns we didn't intend. If your training data is biased, the network will learn that bias. If your data contains weird coincidences or spurious correlations, the network may latch onto those. For example, if your cat pictures always or very often had a coffee cup in the background, the network might learn that without a coffee cup in the background, it cannot be a cat. If you give it data that's very different from what it has seen before, it can fail in strange and sometimes dangerous ways. Neural networks don't know why a pattern exists. They just know, when I use this pattern, my error goes down. So when people say, the AI said it, so it must be true, that's when I start to twitch a little. Neural networks are powerful tools, not crystal balls. They can extend our abilities, but they can also amplify our mistakes if we're not careful. That's why understanding how they actually work isn't just nerd trivia. It's part of being an informed human in a world that's increasingly run on these systems. Let's rewind and recap. A neuron in a neural network is just a tiny calculator with inputs, weights, a bias, and an activation function. It mixes numbers and spits out a result. A neural network is a bunch of these neurons stacked in layers. Each layer transforms the data a little bit more, step by step, from raw input to final output. Training is the process of letting the network guess, measuring how wrong it is with a loss function, and then using backpropagation and gradient descent to adjust the weights over and over again until the network gets good at the task. Deep learning is just neural networks with more layers, more data, and more compute, which allows them to handle very complex tasks in vision, speech, language, and beyond. And at the core, a neural network is a pattern compression machine. It doesn't store every example. It learns the patterns that tie those examples together. It's not a magical brain, it's a very powerful, very complicated pattern recognizing calculator. If you understand that, you now have a clearer mental model of neural networks than most people talking about AI at parties. Please use this power responsibly. Now, if you're thinking, okay, this is cool, but how do we go from these neural networks to those giant AI systems that write essays, code apps, or chat with you? That's exactly what we're doing in the next video. In the next episode, we'll take this foundation and build up to large language models, what they are, how they're just supercharged neural networks, and why they sometimes sound brilliant and sometimes completely make stuff up. If you enjoyed this, hit subscribe, give the video a like if your own neural network found it useful, and drop a comment telling me which part finally made neural networks click for you. I'm Dr. Dude. Thanks for hanging out with me. I'll see you in the next one where we teach machines to talk.